All right. So I'm just going to go over this prime factorization tree. In one of the previous videos, I've shown the code stack for it, sort of briefly looked at some of what's going on inside. And what we'll do next is just type up one of these so that so that you're equipped with some SVG meets MathML skills, as it were. And there's not too much to it, so let's get into it. All right, so the context, of course, is the fact that every not one natural number is either a prime number or a composite number. Composite numbers may be factored as products of primes. And then we're just going to work out how to generate. And I've got most of the values for the attributes worked out already. So, okay, cool. So we're going to have two math elements inside of this div, inside of this division. And the first is basically the product that we want to factor. And then I'm going to designate each of these indicators as an element, which is an element of the set of natural numbers. An element of the set of prime numbers. An element of the set of whole numbers. Integers. Rationals. And an element of the set of real numbers. Great. The next element is going to be an index. Which is a numerical label. Okay, and that is the subscript label. We can just copy this guy. Okay, the next element's going to be, in fact, an exponent. All right, so that's the product that we're factoring. Okay, so we're going to put in our first factor. Inside we have the variable of p sub j, which is an element, p, as an element, once again, the natural numbers, the primes, the whole numbers, the integers, the rationals, and the real numbers, set of real numbers. And then the second element or indicator, math indicator inside of this subscript is all right. Okay, so the next, and then we're just going to put in, which is a replica, really, of this one. So great, just copy and paste that. And then what's needed next is just closing parentheses. So this is the left side of the equation sign. So what we have p sub k raised to the second power. Okay, p sub k raised to the power of 2. And then we have an opening parentheses, and then inside of that parentheses we have the quantity p sub j times p sub j. Okay, which I generally refer to as a variable functor. Okay, great. And then next we have just the expansion of this expression, all right, which is basically p sub k times p sub k times p sub j times p sub j. And so while we're at it, let's go ahead and split the screen and do a simultaneous preview of what we're doing. All right, so of course I should have opened with that, but nonetheless, that's what we'll be doing. Okay, so you can see what we've got so far. And it looks like, I guess this is the reason why we're doing it, right? Okay. All right, so yeah, let's do some live previewing as we go along. Okay, so far so good. That this first factor is variable p sub p sub k. All right, and then we can really just start copying and pasting the rest of them. But before we do, we're going to actually add an operator. The operator mid-dot. Midpunkt for the German speakers, which is a functor. The attribution multiplication. Okay, great. Okay, so there we have our final result, essentially. Okay, so that's what the factorization tree is going to be, I suppose, in a sense, visually proving or demonstrating. Is the sort of structural relationship between these prime factors. Okay, so I SVG is pretty straightforward. It's really just we're drawing a few lines and we're just making sure that our calculations, our computations are accurate in terms of where those lines begin and end, respectively. But before we get to the SVG, I suppose I just need to put in the arrow. Okay, to the SVG. Hooray, we made it. All right, just some attribution. We're going to go with load constituents edges. Okay, and let's go with height of 165. And a width of 200 pixels. All right, and so then in this case, I will put in a sort of explicit comment as a way of labeling each of these layers of the tree. So we'll go with layer 1, which is going to be the root branch. We'll call it the 0th generation. And the ordinals, meaning the order of the branches, this is a bit incidental, just happens to be the way in which I coded up this structure, but it's going to be left or right, left in terms of the order. If that's not clear, it will be in a second, don't worry. Okay, so all that I mean is this first line here is in fact going to be the right edge of the initial shooting from the root node. So we'll see that in just a moment. All right, and then we can just double up here. So 1628, which is this origin point right here, so that's fine. And then we're going to go with 15 x2 1545. There we go. Looks great. All right. Layer 2. Subsequent branches. First generation of the graph. And by the way, I have spell check turned off currently, so if you do see any sort of spelling errors, yeah, just bear that in mind. I'll maybe turn it on in the end and see if we have any in here. Once again, ordinals right to left. In terms of order of appearance. Great. Okay, there we go. So 105, 80, 148, 100 for my tertiary line. Okay, so this is going to be the terminal or crown branch or set of branches, pair of branches. And for the second line, we just need 100 there. Great. Okay, so that basically concludes the branches. Okay, each of the 3 layers, and all that's left is to add their nodes. So the loaded constituents are going to be the nodes of the graph. We're going to display this absolute. And again, we can think of this as a sort of escape character or an escape expression. The rendering engine essentially ignores it, so it has no bearing on the rendering of our tree, and it's there to support the alignment of our elements. This particular tag in this case. Yeah, so the nodes, and again, this is purely just how I ended up coding this up. So you can absolutely experiment with, or improve rather even, the arrangement in this element structure, the arrangement of each of the nodes. I just happen to code them up in this sequence, and so therefore what I'm doing right now is I'm adding the nodes of this 3rd layer, if you're counting from above, from the origin. So layer 1, layer 2, layer 3, and I just ended up coding these nodes first in this sequence. The edges first, the first thing that I did in terms of generating this factorization tree. And after I completed those, then I went ahead and started working on the nodes. And actually what I did last was code up this initializing expression. So somewhat of an ad hoc sequence, but like I said, by all means, feel free to go ahead and improve that. So, but just so you know, what I'm doing next is I'm going to be coding up, I believe, this guy first, then this guy, then this guy. Something to that effect, but we'll find out in just a moment the exact order. Okay, so the first one happens to be the terminal node. It's this last guy. This is the rightmost extreme node, so this last guy. And then the semi-terminal node, and then the subsequent node, or the subsequent node. Terminal, semi-terminal, subsequent. Okay? Or subsequent. All right. So that's going to be the order of operations here, so to speak. Elements. Okay. Okay, and what do we have inside? Well, we have 2 elements. So we have P, which I can grab from up here. In fact, I can grab both of these guys. And push them in. So there you go, P sub j, easy enough. Good. So we've got our terminal node, we've got our semi-terminal node. Next we'll add our subsequent node, or subsequent node. Okay, so we've got our crown branch done. Okay, so we have, for layer number 2, we're going to start with semi-terminal. Start with the semi-terminal. And next will be the subsequent. node. So we're starting with our semi-terminal node, subsequent node, so semi-terminal node, subsequent node, and then lastly for layer 2, it'll be so yeah, let's make sure we understand the sort of, I suppose, the sort of naming logic, a good naming logic to be mindful of. So this node here, which is the terminal node of layer 2, but it's the subsequent node of the terminal layer. So how can we capture that logic in terms of attributive annotation? Okay, so my solution for that is simply to say this last node is not the terminal. So again, this is the second layer that we're going to work on next. It has 3 nodes. It has a semi-terminal node. Well, it has a subsequent node. It has a semi-terminal node. It happens to, and it has a terminal node. Okay, with regards to its own structure, but that terminal node happens to be the subsequent node of the terminal branch. So we'll just go with this encoding, and by all means, feel free to come up with one of your own, but I will refer to it as a sort of phantom terminal in some sense. All right? Okay, and so for this semi-terminal node, the second layer, we can actually recycle this guy here and just give it some updated values in the style tag. So what values do we need? In this case, we need minus 225. So minus 225 and 55. Great. All right, so that completes layer 2. Okay, so there we go. That pretty much concludes the structure. Okay, so if you have any questions, feel free to comment in the comment section below, or just reach out to me via email or direct message, and I'd be happy to just sort of give a bit more insight as to what decisions I've made here. But hopefully that's pretty clear and straightforward, the approach that I've taken. And if you agree, definitely feel free to give it a like and subscribe. See you in the next one.